Right. So yeah, I think the naming for instruction fine tuning, some people call it instruction tuning and so on, but I'll just call it instruction fine tuning. Doesn't really matter. And so the outline of this talk is that so this is kind of the big structure of the current large language model training setup. So we start with the pre-training, and then we do instruction fine tuning stage. And then we do the RLHF, which composed of two parts. First is the training of the reward model. And then using that as an objective function, we train this policy model. That's the kind of the policy gradient that was covered in your last lecture. And that one is the final artifact. We use this policy model, for example, like ChatGPT is a policy model, and that will be the final artifacts of all this training. So in today's lecture, we are not going to cover pre-training, and we are going to first look at instruction fine-tuning, and then we'll look at the reward model training, or RM, and then finally we'll look at the policy model training. So let's start with the instruction fine-tuning. The high-level idea is that we frame all natural language tasks in the form of natural language instruction to natural language response mapping. So the best way to understand this is to think about what we have been doing before we had this instruction fine-tuning idea, and maybe using a concrete example to illustrate this. So let's use this example task from Blue benchmark, which used to be quite popular. So this one is from COLA. So given a sentence, the model has to figure out whether the sentence is acceptable or not. So it's a binary classification with 0 representing that it's not acceptable. So if we think about this as a machine learning problem, we have input is text, and the output is the label, direct 0-1 classification label. If we use models like BERT, this is like going back to 2018, we have to have BERT is like a general encoder system. So the output of the BERT will be embedding space vectors. So we need to project that to output space, which is 0-1. So typically we can kind of put it into a sigmoid and so on. So we need linear layer, which is specific to this task. So if we want to learn another task, we need to have another parameter added, fine tune the whole thing, and so on. So that's kind of the status. Now, T5 came along a year after, and it did a lot in terms of unifying the architecture. So the only change you can see is that the output was changed from label to text. So now the model outputs just the string itself. And that really unifies all the tasks. So you can do text to text mapping or sequence to sequence in more generally. So here, because we every task is just text output, we don't need to add any additional parameter like a task specific layer. So you can say that the architecture is unified across task. But now, because everything is same, we don't need to have any other extra parameter. Why not try multitask learning? And T5 was actually on multitask learning. So here is another task from Blue STSB. In this one, we are given a pair of sentences, and then we have to figure out how similar they are on the scale of 1 to 5. So given the two sentences, the model outputs the score. So if we want to multitask, like put these two in a same batch and train it, what we need to do is let the model know how to distinguish the two. Otherwise, it doesn't know how to do that. So the way T5 did it is to add this metadata, like a COLA sentence colon, and then the sentence comes after that. And for the STSB, it's actually even worse. STSB sentence 1 and sentence 2 and so on. So that way we can kind of, at the inference time, we can put in those trigger words, and the model will be able to follow whatever it's used to answer that question. So this made T5 multitask learn fine, but we can see that it's quite arbitrary and tasks are not semantically related. So at this point, instruction fine-tuning came along 2 years after that. And here we go one step further in that we still do text-to-text mapping, but here we are removing this metadata and using a unified format, which is just explain the task in natural language. So it becomes a natural language instruction. So in the case of COLA, we can do, is the following sentence acceptable? And that's exactly how I explained to you when I first introduced the COLA task. So That way we can just answer in a little bit more natural language way. It is not acceptable. And for the other tasks, we can do on the scale of 1 to 5, how similar are the following two sentences and get the two sentences. So again, same as I explained to you. So why not explain that way to the model? And now there's no such metadata. And what we can hope is that from the perspective of the model, it's just responding to the natural language instruction. So I'm just following that. And for an unseen task at the test time, it can just follow the instruction as long as it understands what it's doing. That's kind of how the generalization is done. So we can say that the tasks are unified and it's just represented as a natural language instruction. The model can hope to answer it. And so in a schematic diagram, here is the idea. So we bring in this general knowledge from pre-training, very powerful pre-training model, but hard to use. And we add this instruction fine-tuning stage just to teach how to respond to natural language instructions. And that is how the generalization is done. So I've seen many talks or papers about instruction fine-tuning where it's kind of framed as, okay, we do this idea and then the model performance goes up. I think it's quite important to understand why the intuition behind why this generalization is done. So natural language is really nice way to unify all the tasks and just let the model respond to instructions. In terms of the compute, instruction fine-tuning is really cheap compared to pre-training. And typically it's about like 1% or sometimes Flan Palm, I think was like 0.2%. So that is not, so we can probably think that we don't teach anything non-trivial during instruction fine-tuning stage. Most of the heavy lifting is done, most of the knowledge is coming from pre-training. We're just adding a little bit of the layer so that the model can activate what it already knew from pre-training. So that's pretty nice because we don't need to put in much compute and it actually makes the performance much better. So in terms of the alignment, alignment is kind of a very popular topic nowadays. So we can think about this instruction fine-tuning as an alignment problem in that we are aligning the models to follow the human instructions. And, oh, sorry, that was wrong. So now this instruction fine-tuning is a very popular idea, and there are a few different ways of doing this. And I can kind of group them in two different flavors. This is just very arbitrary, my own definition. I don't know if anyone else uses this definition, but I think it's clear to do it this way, and that will kind of show what the limitation of the current build is. So first flavor is the instruction fine-tuning on a mixture of academic tasks. And the notable ones are Flan, 2 papers on that, T0 from 2021. And the second flavor is on the instruction fine-tuning on user prompts, like ChatGPT, API, you give the prompts, those are the user prompts. And then we can write like a instruction, the response, human can write that and fine-tune on those. So we'll go into each of these. So let's start with the first flavor. So when we try to improve that instruction fine-tuning on academic tasks, what are some of the things that we can control? What are the scaling knobs? What can we scale? And there are 2 things: number of tasks in the academic task and task diversity. So in the example before, I showed adding 2 tasks, right? STSV and COLA. But wouldn't it be better if we add more so that the model can see many different types of instructions to response mapping? Then it can probably generalize better to unseen instruction. So that's kind of the idea. And we'll see some extreme version of that. And when we add more tasks, if all the tasks are very much similar, say 100 sentiment classification tests, Amazon reviews or movie reviews and everything, then it's probably not going to help much on generalizing to unseen test types like translation, for example. So we also need to make sure that we cover many different task diversity. So starting with this one, this is the Flan scaling Flan paper, which introduced the Flan T5 and other things. Here, the idea is that we know that this instruction fine-tuning works. And it works because of this generalization that I mentioned about. So why not just put that into an extreme scaling? That's kind of how Google always works. Simple idea, scale up, and then see what happens. And so that was, we put pretty much all the academic tasks we could find, 1836 of them. This is, I think, still the largest number. And this has many, many examples. We don't even cover one epoch of each. So these are the task types. You can pretty much think anything that you know will be there, question answering, whatever. And this thing, the COT, reasoning, chain of thought, will be quite a different type from other things. So I'll come back to that. So that's the task mixture. And then here's the result of that scaling. So whenever we think about this general idea that applies to any language model, the most important thing, in my opinion, is to show the scaling behavior. So if I show this idea works in one scale, the very natural question nowadays is to see, does it scale? If I try that on the larger scale, does it work? In many cases, it doesn't. So here we show with the three internal models, 8 billion, 62 billion, 540 billion dense model that were trained all on 780 billion tokens. Now, in current scale, that's not really the largest model, but still last year was pretty big enough. So we should pick those. And then let's start with this gray line. This one is the just pre-trained pump checkpoint, no fine tuning. And that is the performance on some things. So for this lecture, let's not get into details. So here, y-axis, you can think about it as a carefully chosen average number of 6 different benchmarks, but each consists of like many, many tasks with hundreds of tasks, carefully averaged. So let's assume that represent the capabilities of the model relatively well. And so we can see that it's really difficult in that 8 billion parameter model. It's getting less than 10% on this, and scale matters a lot. Now, as we get darker blue, we add more tasks, starting to 9, 89, and so on. You can see that the performance goes up almost monotonically. And that is quite a big difference, because here I would like to point out the scale of this plot from 0 to 60. So we're talking about like a double-digit gain on almost all cases. That's the first thing. So scale matters in both the number of parameters and the number of instruction fine-tuning tasks. But also we see that after we add 282 tasks or something, then it doesn't really help much. And that was quite interesting. And actually the same data, if we just change the number of axes, the x-axis to number of fine-tuning tasks, then you can see that diminishing return a little bit better. So the hypothesis we have for why this might be happening is that these are academic tasks and they are pretty much similar. Once we have 282 of them, we don't really add much diversity. And that's why this scaling this diversity matters as well. So that's the hypothesis. How do we try to at least sketch out the proof of this? We'll do this evaluation on the chain of thought or reasoning. So I mentioned that the chain of thought is a kind of a different types of tasks among the 1800 tasks. So we are going to train 2 models, one with the chain of thought, one without, actually 3 models. So let's again start with the gray line. That's the pre-trained model. And on the y-axis, in this case, we have a performance on the reasoning benchmark. So those are measuring the reasoning capabilities. So let's start with this green one. Compared to the gray one, if we fine-tune without the reasoning data in the supervised data set, we get really, this downgraded the performance of the reasoning, and it's almost not working. So that is quite surprising. What it's saying is, even though we have about 1829 or whatever, 1800 tasks, the model cannot generalize to unseen task type, which is the reasoning. So having more doesn't always help. In contrast, if we just train on 9 reasoning tasks, the red one is actually better than pre-training. But if we train on both reasoning and the remaining, the original flat idea, then we get better than either cases. So that's a quite nice solution. What about on the non-reasoning performance? So this is performance on the non-reasoning benchmark. And if we just do fine-tune on reasoning data, then the performance is almost the same or even worse than the no fine-tuning pre-trained model. And if we train on both, actually it's the best solution, even for non-reasoning. So this shows that if the model hasn't seen very different task type, then it cannot generalize. And just having a little bit of that is enough to cover all cases. So test diversity really matters for the instruction fine-tuning idea. So, sure.
So does that mean from pre-training the model didn't learn reasoning? It has to learn reasoning from this fine-tuning.
I think it did learn to reason. My hypothesis is that instruction fine-tuning is kind of activating the behavior. And if we really work hard on crafting out the fuchsia prompts here, I think we can probably get similar to this. It's just an easier way to activate the model's performance. So yeah, but I think it's just kind of a, you know, if we don't fine tune on that, it's not activated. Yeah, so this first flavor of instruction fine tuning on academic tasks, what is it good for? I can think of kind of the 4 different categories. First is that it really improves the language understanding task as opposed to language generation task. And it's also very good at cross-lingual transfer. I didn't cover it here, but the flat paper covers that. So what that means is that we train on following the English instructions, then it can transfer to following different languages. And it's actually really good performance on those. And third, we have shown that this idea helps almost all models that we have tried. We have tried T5 small, 80 million parameter, all the way up to 540 billion parameter. And in all cases, we have seen non-trivial performance boost. And we covered encoder-decoder model, decoder-only model, and different pre-training objectives, and all that helped. So it's really general method, and we don't really see this kind of a general idea. So when I was at Google, whenever some people came to me and asked, well, should I try that? I almost always say this will probably help. And that's a really strong statement to make. And then finally, this was a recent work in one of the co-authors at MIT. He carried out this work and realized that many people still don't use like a GPT type of model for prompting. They still use, especially in the production setting, take the SPERT kind of encoder model, fine tune it further, and work on their own problem. Even if you do that, you can still initialize from the instruction fine-tune version that is better for single test fine-tuning. So with this, we can probably say if you're using something like T5, just switch to plan T5 and nothing changes, it'll probably improve the performance by some, that's a kind of a free gain. But those are the good things. What does it not do well on this first flavor of the instruction fine-tuning? It's not great for long form generation. So because that is the limitation of the data set. So academic tasks have this inherent limitation that they are long inputs and short targets. And because of that, the model doesn't learn to generate long stuff. And if we think about most of the interesting applications of the language model that you have seen in Twitter, news, whatever, they tend to have a very long generation. And so this instruction fine-tuning flavor cannot be helpful for that. So here's one demonstration of that. So in this fun 1800 tasks, I plotted the length distribution of the input on the top, target at the bottom. So you can see that input is quite long, all the way up to like 2,000, and then target, most of them are like 100 tokens or shorter. And even like scale is just mostly translation task that doesn't help much. So this is kind of what happens if you use academic tasks. And why is that? It touches on this very kind of an important idea that we don't have anything that can be used reliably to measure a arbitrary length string. So when we do like a question answering or some like a task that outputs the string, we need to do like an exact match or F1, which only supports like maybe 10 tokens or so. If we have like the 2,000 tokens that are generated, there's no way to measure it in a nice way. So then all the tasks are like designed to be this way. Question?
can we continue retraining of this in the instruction finding phase and make the input with the long form inputs?
Yeah, so that's actually one of the things that InstructGPT will cover later in Greta to mitigate the degradation. Some people call it brain damage on this academic data set. Or some people call it alignment tax. But yeah, we haven't tried that, but that typically helps. But not solve the entire problem. So this is covering that. Yeah, the target length is short, and in my view, the entire research field is bottlenecked by not having a reliable way to evaluate the model generation that is long, and that is still very open-ended. And I've been inviting all the people in the academia to think about this problem, because ChatGPT or other models are generating very, very long, interesting text, but there's no way to really measure that whether it's good or bad. So we can not really iterate on the research ideas fast enough. So as a field, we should think about it. Now let's go on to the second flavor, which was training on the user prompts. So what are user prompts? So if you try out on like a couple of years ago, GPT-3 API, you type it on the text box, those are the prompts, and that represent how people use language models, and they are quite different. Here are some examples. Explain the moon landing to a 6-year-old in a few sentences. Write a story about a wise squirrel. You not see this kind of prompt in the academic data sets. And what is different is that it's already like saying 2 sentences. We don't have a way to measure stuff like that. And then story will be inherently long. So those are the user prompts. What we are going to do is, yeah, put this into a supervised learning setup just like before. But so the inputs are from the user prompt, but we don't have a gold answer. So what they did for the InstructGPT paper is that they put human labelers and write out the demonstration. So they call that demonstration. And once we have like, I think 30K examples of such, we can train it. So that's the instruction fine tuning, second flavor, more modern one. And here is the result. So we are comparing flan T0, pretty much similar. The original version, this is not the recent one with the flan T5, but still I think the idea is the same. And SFT, supervised fine tuning, this is kind of the OpenAI language. I might be mixing SFT and instruction fine tuning because I got used to this. So this is the instruction fine tuning flavor 2, flavor 1. If we compare these two, then we can see that it's slightly better. What is the score? So we bring in some held out user prompts and then let these two models generate the stuff and let humans evaluate. Human evaluation is the key here. Which one they prefer, which one they like. And it's prefer the ones trained with the human demonstration. So that really shows that academic tasks don't represent what we care about if we use this language model as a language API, which seems to be increasingly the case. Yeah, so we have seen some evidence that instruction fine-tuning is highly effective, but it has some inherent limitations, and those are understanding them is really important. And I think I'll probably try to spend enough time on this lecture to highlight that. So to understand the limitations, we should go back to, there are many issues. Actually, I can probably put in some additional reading, but this is just my personal favorite limitation. So what is the learning objective in the instruction fine-tuning? So we are using, for almost all language models before RLHF, we have used maximum likelihood as the objective function, meaning that we, for a given input, we pick this target and say, this is the single correct answer, everything else is not correct. That's a very strong statement. And in RL, this is called behavior cloning, which I think is more descriptive term, because we're trying to let the model clone whatever is in the target. And the hope is that even though we're kind of saying this is the only answer, if we have a lot of those for many different inputs, hopefully the model can learn to generalize. And in practice, this has been the case, and that's why we have seen a lot of advances in the language model space. But what is limiting is that this kind of setup requires formalizing the correct behavior that we want to teach the model. And let's think about this a little bit. So formalizing means like if I want to teach something to the model, I need to know how to formalize it well. But this is not always that easy. So let's do some, some exercise here to think about. So our job is to think about what is the correct answer. In this case, the input is 2.3, very trivial. So the only possible answer for this one is 5, and it's not really ambiguous. So that's great. Let's increase the difficulty of or ambiguity of the inputs. What is the sentiment of I should have studied instead of watching this movie? And in this case, most likely it's a negative, but I could also say maybe this was so interesting that I could not just close it. So maybe positive, but this is a little bit more vague, but still relatively easy. Now, maybe you can think about even more vague thing, translate this Korean, that same sentence, and then translation of this much length is kind of open-ended in that I could have translated in different ways. If you think about translation of a whole paragraph, it can be multiple answers. Now, let's go into even more extreme case. Write a letter to 5-year-old boy from Santa Claus explaining that Santa Claus is not real, convey gently so as not to break his heart. This is actually one of the examples that people tried on ChatGPT, and I kind of rephrased it myself. But for this, can you find a single example that you can confidently say to the model that this is the right answer, everything else is wrong? I think this is getting not trivial, and we don't really know what we want to teach. We just want some vague notion of what we want from the model, but not enough to formalize it. And maybe a little bit more realistic one, implement logistic regression with gradient descent in Python. That's kind of my favorite whenever new language model comes out. I try that, and it's actually pretty good. Like it writes out all this like a object-oriented style. Sometimes I can do a functional style too. Works really well. And then, but there are many different ways, right? I just said object-oriented style, functional style, whatever. You can use like PyTorch, or you can use NumPy only, and so on. I don't think there's a clear answer. And do we want to teach the model one of them? I think there's really not a good answer to that. So as we have seen in this exercise, the more interesting behaviors that we're trying to teach the model is getting more vague, more abstract, and more open-ended. And that's for a good reason. And so, yeah, let's make some observations. Increasingly, we want to teach models more abstract things, and therefore, this objective function of saying this is the single correct answer seems to become the bottleneck of the learning process. And so, if we think about why this is so limiting, maximum likelihood objective, or equivalently the cross-entropy loss, is a predefined function. So if I give you the correct label y and model prediction, say y hat, then there's one number that comes out of that function, because it's just the defined function, and there's no learnable parameters in that loss function. So can we make this more expressive and actually parameterize this and the objective function and learn it? That's kind of the key idea to think about the next step. And RL provides one way of using a learned objective. So in reinforcement learning, we try to maximize the expected reward function. I think you covered it in the last lecture. So this is a very general way of saying that how the reward is defined is just, the problem's specific. But if we think about it this way, this reward is the objective function of this learning problem. So if we use a learned reward, then we're using learned objective function. To make it maybe more clearer, if we think about a RL agent playing a game, then we get like a +1 reward if the agent wins a game, 0 otherwise. This is kind of a valid reward function, but it's not learned because we just prescribe 0, 1 in under different cases. What we want to do is make a model neural net that encodes this reward behavior. So what do we do well? As a field, we know how to do this thing very well, which is that use the neural net, very big neural net, to do supervised learning on relatively well-defined problem. This is what the expertise of humanity at this point. So why don't we try to use this, what we do well, to learn the reward model? And that's the idea here. And that's the second part of this lecture. So let's go into the reward model. I'm going to call it RM. So in this second, like a 2/3 of the lecture, the theme of the lecture is that I thought about maybe there are so many RLHF papers, and this is the hot topic nowadays, and there are many variants. Instead of covering as many of those variants and papers possible, I will cover the foundational ideas. And if you internalize those well, then I think reading those will be very trivial, but not the other way. I think this is always the right thing to do. Just find the foundational papers and read them very, very carefully, understand and internalize. So in this particular case, we are going to follow this InstructGPT paper, which covers, popularizes RLHF, and very similar to what's done in ChatGPT. So reward model training. To think about this, I think the best way to understand is actually look at the data and see what is input, what is target. So here we can go back to this example from the InstructGPT. Explain the moon landing to a 6-year-old in a few sentences. And in this case, we are going to do a comparison. And the high-level question is, which completion is better? By completion, I mean model generation. That's kind of a also OpenAI language. So completion 1, we have some stuff, completion 2, and we let the model, reward model, to compare them. And here I wrote something, the moon is natural satellite of Earth and whatever. It's valid, but it doesn't really answer the question about moon landing. It's just talking about the moon. And here is the correct answer, or better answer. And then it's talk about the people went to the moon and they took pictures of what they saw and sent them back to the Earth, so we could all see them. It's really like 6-year-old language, and it talks about the moon landing. So in this case, we can say this one is better. So that's kind of how we want to train the RM model. It's very vague. I'll go into how to formalize this notion. So, and this setup, from the perspective of the alignment, we are trying to align the models to the human preference. So I think Anthropic calls this preference model, PM, but more generally, this is a reward model encoding the human preference. So why do we want to do it in like this pairwise setup instead of in one completion at a time? So let's go back to the trivial example, 2 + 3. In this case, let's say one model output 4, one model output 5. In this case, it's so clear that you don't have to compare them. You could just see this one and say, oh, that's correct. And then this one, that's incorrect. You don't have to compare in a relative manner. But what if we go into, again, this Santa Claus example, and then you have some completion, I didn't write it because it's going to be long, and then another completion, both are good. And can you evaluate independently? Or if you do a comparison, would that be better? I think it's much easier to do the comparison because that's kind of doing it in a relative manner. Another example that I kind of like is if you're evaluating the code writing quality of the model, you can maybe have like a logistic regression implemented in one way, another way, and let's say both work, and one is better in a stylistic manner, then you can kind of prefer this one. So that's really easy in a comparison way. But if you were to evaluate both of them, you might give them both good answers, and then that wouldn't compare that stylistic difference. So that's kind of the comparison, why we're trying to do comparison. And as we went from easy to very difficult prompt, comparison made more sense. I think we'll be prompting the model even more difficult than this, a lot more difficult, and that's increasing quite fast. So this comparison probably will be more useful and increasingly so. So let's get into how we actually structure.
So in your previous example, wouldn't the comparison makes the model performance on the more deterministic task worse, like for example, for the arithmetic?
Yep.
What you want to convey is 5 is correct, everything else is wrong. But doing this comparison actually teaches model that 5 is better than 4, but 4 is wrong.
Yeah. So we shouldn't have this kind of thing in the comparison data set. Comparison data set should, this should be like in the SFP or maybe just coming from the pre-training. But for what I was trying to say is like why do we do comparison? It doesn't make sense as you just point out in this kind of easy case. It only makes sense for difficult case where there's like a clear, like two things that really work well for the reward model is when there's a clear winner and that's not easy to evaluate like right away. That will be the good reward model data. But this is also very new research, and I think the reward model data is like not clean at this point, but yeah, definitely I wouldn't put that 2+3 or anything that easy there. Does it answer your question?
Yeah, so RLHF is more focused on this hard or complex.
Yeah, I don't think there's like a clear answer to this kind of thing, but at least that's how I would think about if I'm doing comparison setup. I think it makes more sense to do more vague or hand wavy things. Yeah. Or the easy ones, the models already do very well. So I don't think we should add in more training and always compute. It's like pre-training already solved most of the easy stuff. And that's kind of the domain of the scale. Scale really solves all those, and we should just focus on this vague behavior. So let's get into some of the math. This part is, so we just talked about how to do the preference modeling and align the model to the human preference. And how do we do that? So let this function R, the reward, take in two things. X is the prompt and Y is the completion, the input target. And then the important thing is that this function R is parameterized by the parameter T. So that's going to be the reward model neural net. And the output of this, the codomain of this function will be the scalar. Takes in two things, output scalar, because that's what the RL requires. So how do we actually implement this in practice? So again, following this InstructGPT paper, we take out the language model, decode only say GPT-3, and then the last layer is like an unembedding or output embedding. We can remove that because we don't use it, and then just take the logit of something, like maybe the last token or something, and then we can project it down to with a linear layer, and that gets the scalar. And if we train it with that, that will be the way to do. That's actually how the InstructGPT did it in the paper. But implementation doesn't really matter. You can do it in other ways, but as long as you have enough capacity, it's fine. And this is kind of using it more like an encoder because we're taking out this unembedding layer that is used for generation. So it's more similar to Bart if that helps you visualize it. So
Embedding of the master, or you average embedding
I think both can be done, or you can use like in like a BERT, you have like a CLS token in the beginning, something like that can work, but also you can use like a different Sentinel tokens or whatever. The InstructGPT paper doesn't even mention how that's done, but I think probably doesn't make much difference. Okay, yeah. Now that was the objective. And then sorry, this is the objective function. So let's call this Pij, the probability that completion yi is better than completion yj. So we were talking about this modeling the comparison. So we need to be able to formalize this notion of probability that one is better than the other. And one nice thing about log of odds is that it's kind of balanced and so on. So we use this very old Bradley-Perry model from 1952 that the log of odds, which one is better, is modeled as a difference in some scalars of each thing. And in this case, we just say difference in rewards give the log odds. This is the model. And like, if you don't find it intuitive, that's how we model how we are going to encode the comparison. And this is not really covered in detail in almost all resources I found. So when I learned it, I was kind of confused. So the way I think about this is that you are comparing two things. And if each thing has some scalar that represents the strength of this completion or whatever the thing, then we use those scalars to compare these two. I think one interesting is like maybe doing like a NBA game. We want to compare the teams and want to find out the probability that this team will win this game. Then we can think about the scalars that represent the strength of each team, and we can kind of model this way. that will give, if there are n teams, then we'll need only learn n parameters. If we do it with the more of a brute force way, then we will need to learn O n squared, each pairwise probability. So that's kind of the intuition. Let me know if you find this. Yeah. Then data is not really helping. I mean, it always happens, but if you actually look at the SFT, the interesting fine tuning data, that's also there. But I think it's model can kind of ignore it, but or we can say it's a regularization or noise. Yeah, so I think both are bad, but if this is like one is less worse than the other one, I think that can still make a good case. Actually, the RL is really good in that we can have a negative. It's really easy to have a negative example. In your previous lecture, there was like a policy gradient. You have like a reward times log of policy probability. And if you think about it like the maximum likelihood, it's like a weighted version. If this sample has a positive reward, then we push up the probability of that sample. If it's bad, then push down. So because RL is really good at having this negative sample encoded, maybe having two bad ones, one being slightly worse, could be okay, but I haven't really thought about that much. Yeah. Question? Yeah, so in the GPT paper, what they did was not like, I'm just to talk about this like the fundamental idea. What they did is like they put in, say, one prompt to k conditions, let's say 10, and then you just pick two at a time, so 10 choose two, and then you get like 10 choose two example. But if you put them in like a series, if they go into subsequent batches, that will be overfitting to that prompt. So what they did is like put everything into a single batch so that when you do the gradient update, only one update from that. A little detail, but that's how things are done. Okay, so once we have this log odds, we can solve for PIJ. This part was the modeling, this equation is the model. The second part is the rearranging, solving for PIJ to get this. And for machine learning people, this kind of looks familiar. That's the sigmoid. So PIJ is modeled as a sigmoid of the reward of yi minus reward of yj. And the order matters because we're saying this is better than that. And that's the probability that it's important. And once we have this probability, which is what we want to do what? Maximize the probability that this thing is better. So we do log prob maximization and using the data from the comparison data set. So here, what is being maximized is the reward model parameter, and that is simply standard supervised learning, which neural nets are really good at. So that's kind of how it's done. One important thing is that here, where is the human person coming from? It's in saying out of these two, yi is better. So I'm kind of using this yi as a winning one. Some papers call it W and losing W and L. So whatever you put as reward the first term in the sigmoid, that is the label. So if you change the label, you can swap them and so on. Yep. No, I don't think it's like I can see this is the 1952. I think yeah, I was gonna exactly say this in the next slide. But maybe I'll come back in the next slide. Question there.
In practice, doing the company once you say that you want more data.
Yeah.
So during the inference time, we kind of get like multiple completions and send it to the reward model and try to get the completion of the reward. You also use it. Is that how it goes?
No, actually, that could be I'll come back to it, but when you do like a RL training, you only send one thing to the reward, right? You get the reward, backprop, and train. In practice, we are encoding this reward model preference to the policy model. So another way to do it is like you just take the supervised checkpoint and then generate 10 things and then get the reward and pick the best of one of them. That's called like a best of N model. And if you look at WebGPT paper, they did this. This is kind of doing RL at the test time. So it's called the test time compute. And that was actually better than the RL. And not always the case, but this is a really good way to test out if I do RL on this, can I get more out of it without actually training RL? So yeah, that's a best of N modeling. Yep.
That's a bit more about the data set that we need to like
You mean like the comparison data set? But in what aspects are you asking about? Like what types of comparisons there are?
like it is, and whether there is any medical about, I guess, the people that I do.
Sorry, like qualitatively, what types of comparisons do we have?
So like, I feel like, there are questions that would be like pretty hard to answer.
Yeah.
And we really be depending on, who are the person answering the question. Like, for example, like, it is like, who's your favorite person? Right, things like that.
Yeah.
And I'm just wondering, what kind of data set do you use and how do you make sure that it's like open-ended?
Yeah, so that's a very open-ended question at this point. I think one, maybe I can point to, like, I'm not allowed to say what we do actually, but one public paper that we have is like a Anthropic conversational AI, where they have to avoid the subjectivity in the preference, right? They put out like a 16 principle constitution that they follow to label which one's better. And actually they use AI to do this labeling, which one's better, done by the model. So they call it RLAIF instead of RLHF. So there, what they've done is like given two conditions, you have like, it has to be helpful, not harmful, and whatever, 16 of those, and sample those constitutions, and then using that, label those. So I think that's really good way to do it. And so, because otherwise you kind of come into, if you have a good labeler or disagreeing labeler, the data set will not be consistent and so on. So, yeah, so that answer your question. Yeah.
One follow-up question on that, where do you get the cost? Because it seems the cost is reducing here is very important.
Yeah.
So how do you get the cost?
Yeah, that's, I think, a really, really important one. I guess if you have like a length API, that could be one way to do it. But also, I think the Anthropic paper, if I remember correctly, uses like a synthetic prompts, because once you do like this kind of modeling enough, then you kind of know what are good prompts and what are or what way do you want to train the model for. If you want to train like a creative, make the model more creative, then maybe you can create like a prompts that are like write a story about wise frog that we saw, things like that, and then change out the animal to different things and so on. So I think they're like a popular way, just using this user prompts or synthetic ones.
Synthetic means the model is generated.
Yeah. I think so Anthropic, this CAI, the constitutional AI, almost everything is like done by the model, and synthetic data generation, rewriting based on these principles and so on. So the human feedback is only writing up this constitution. And I think this is quite interesting because we humans can collectively define this constitution. What is that we need to teach the model, and everything else is kind of done by the model based on the references. And that's quite new, like from last like December, and I think it's very popular. So I don't know if that's like the best way, but at least there's quite a bit of ambiguity in what prompts to use, how to label, and so on. There's a very new research field, I would say.
So in that case, how do you know that the model
You could do that. I think it's good. Then you can use the model to evaluate the evaluation model and so on. But at some point, I think people kind of, just try to do some human evaluation for one-off thing, and then once that is done, then you can kind of freeze it and just use it. But if you kind of use the human labelers, there are also many errors, and I think at this point models are probably better labelers than average humans on many of those. So yeah. Oh, question.
One more thing, just to think that, I know it's into the that part of the journey, is the get 10 computers and try to figure out which computers can help you but does it fit into the entire large model like, does it have either way to put it in the generating computers? Even before the computer can plug the
You mean like even before one single completion is done?
Yeah, so basically, we can't use the many second kinds of, and response from the language model.
Yeah.
You can say it on my preferences, and after testing, it can always keep the computer that I prefer.
Yeah.
But if I want the language for which I see output the computer, to my preference, that all.
I don't know any work of that kind, but I think that sounds like a interesting thing. As we get to the RL part, we'll see that we give reward at the end of the thing only. And that maybe is one way to change it. In general, RL, the reward can come in at any time step. So yeah, so I think I don't know any work of that any published work, but seems like a very interesting or flexible way to improve the model. All right, so yeah, so some observations about this RM training objective, the thing I promised you. It doesn't model. Where's it back here? Yeah, it doesn't model how much better one completion is than the other one. It just models how confident the model is in one completion being better than the other. But it doesn't know like how much better it is because it's a so simple objective. And that's why what happens if you like use very old model with just a different. But I think there's a lot of room for improvement for making the reward model better. But I still think this is really important to learn because those are more of a detail. And we'll come back to why that's really important paradigm shift. So let's get into this third part of the picture, which is the policy model training. And this is actually the actual RL training. So let's start with the objective function. As an RL or the policy gradient problem, it's simple to maximize the expected reward. I don't like this kind of equation with the random variable, distributed, whatever. But I try to be more consistent with the reference in paper. So what it's saying is that this same reward function are taking into x, which is the whole token vector, and y is the completion. It takes those two with the parameters, and then it gets the scale. Same thing that we've been using the previous slide. The only difference is that x and y are both are random variables inside expectation to take the expectation. And what they are sampled from d pi of theta. What does that mean? So for x, we use the prompt, the user prompts. That's how we sample x. And once we do that, we can use the current policy, whatever is the data parameter that model is. We condition on this x prompt that is sampled from the data set, generate y. So that's done by so we call that unrolling the policy, or like just trajectory is the terminology in the previous lecture. So we create the trajectory, and then that becomes the y. That's the sample from the data set with the policy by data. That's kind of how it's done. I'll explain this process one more time later on, but that's the general objective, expected reward of completion and prompt. Yep. So what about the training? So once we have that objective, we just maximize it with respect to data. And the important thing is that we freeze the reward model. After training, it's done. We don't touch anything about the reward model parameter. So that just becomes a fixed function. And we just maximize it. And how that is done, again, deep learning is just gradient descent or gradient ascent. So we always use that. So just take the gradient of this thing and iteratively update it. And how do we take the gradient? That is what was covered in the last lecture with the policy gradient. So you can use reinforce like the last one or fancier ones like the PPO. And that's what was used in ChatGPT, and it was introduced in 2016 or 17, but still used. So it's a quite interesting algorithm. But at the end, it's doing this update in a much stable way. So essentially what happens is try to pick a gradient with respect to this data, then what will come out with post gradient process is that you'll just put the gradient inside this expectation by changing the order of that. And then the gradient becomes gradient of log of policy. Policy is the language model. We know how to differentiate that. And so that's really nice. You can do non-differentiable stuff. So that's kind of what happens. So I won't go into the details of the derivation. I think that's kind of out of scope of this lecture. Instead, I'll try to focus on the implications of why this matters, why you should maybe think about learning more about this math and so on. Okay.
Let's say the reward model is playing out something. But now during RL, the model is changing, our target is changing, which would create some distribution shift.
Yeah. Yeah.
Does that matter?
I think it does matter. Because like the reward model knows how to grade the distribution that it has seen, right? And we start with that, but the policy changes. So even though the prompts are the same, like prompts that gets used to RM training and GPO or like the policy gradient training can be same, just held out. But then what gets generated is different. And so it's kind of new out of domain for the reward model. But because the prompts are same distribution, I think it's okay. What's done in practice that kind of slowly change the policy so that it doesn't really do it. But I think it's one of the areas that is open-ended. Like, why not update the RM periodically? I don't know if anyone has done it, but maybe that's just one way. But I probably should mention measure if this distribution shift has a room for improvement. I don't know any quantitative measure of that. Yep.
When we do the RM training, what is how much data do you get? How much is the good training that you
Yeah, I think that's instruction PPT. I think I don't remember on top of my head. Probably like so SFT, the instruction fine tuning was like a 30K or something example, and then RM probably like that 100K or less, like a couple tens of thousand. And then for the constitutional AI, that Anthropic one, I think they did like 100K, but not like millions. So tens of or hundreds of thousands. And we don't really need that much because again, most of the power is coming from pre-training and we're just activating that, so we don't need that much.
If it's not able to do in context learning, because you can always use this RM training to kind of
I'm not sure if I follow. So why, how is it related to context learning?
If I'm planning to use language model as a planner, plan of a certain time, and the plans that user examples are not good. But if I'm able to select like 30,000 examples, but planning starts and the audio writing.
Yeah. And how do you use that for like generate multiple things and yeah, I mean that might be possible, but
because I don't think because the remote one is not plugged into the computer system. Even if you could generate 100 computers, all of them will
yeah.
because it doesn't know the car.
And yeah, and they have to be different enough in the right way and so on. So I think if you're putting the effort to train RM, probably like this to scale up and then like they're using context learning. So questions? Right.
So PTO is from a reinforcement learning perspective is on top is a online algorithm. So this is fundamentally an offline process, right? First, you go to the user and get their feedback, and then you just go once to the user. The user goes to the environment, go to the user, get their feedback, and then you go out. You don't gather any more data. So essentially, an offline problem. So why not use offline rather than the online algorithm policy? Right?
Yeah.
People giving that a thought.
I think that is, Berkeley is, I think, working on that direction. I'm not really familiar with it offline, but I probably am not qualified to answer that question. But I think in the sense that Pulse is generating the data, it's on Pulse. I mean, that's like changing enough. If we're changing the right direction, that's probably okay.
Offline funding research and learning is just different data.
Yeah.
And you're trying to build a policy from that data. And you're not allowed to interact again with the system. And that's basically the situation that they're in there. Kind of thing, and it's going to start to just interact with the users one time, you collect the data from them one time, and then you go out.
Yeah.
If you were to go back again, and after you change your data a little bit,
yeah,
you go back and ask the users again to evaluate once again for some new responses.
Yeah.
Then it would be an online situation.
Yeah. But then like the prompts are just collected like without really interacting. I mean, some biases like the users know the system, so they just type in different prompts, but I think the prompts are not like even if you change the model and try to make it interactive, I don't think that will change the prompt distribution.
So the prompts would be the same, but the responses,
Yeah.
as you change data, right?
Yeah. Yeah.
And so you could give this, to give the users a new set of prompting to, ask them to evaluate this new set, then do the reward model and then.
Oh, yeah.
The reward model.
Yeah. That's a good one. Yeah. Again, like I'm not really familiar with the alternative. But I think that seems like very correct approach to me. So yeah.
You know, like the people have open AI or looking at this kind of thing of most we're going back to the labelers and helping them to.
I'm not allowed to say that.
I'm understanding maybe once you get the once your label is not given, it's like getting that response to that model again is getting really something like that is we do that work.
Are we doing on time? Okay, so yeah, the training procedure. Yeah, I think this part is really at least to me, this took some time to really internalize it. I feel like I understand it, but I think if you understand this part very well, then I think you can kind of think about what are some of the parts that you can improve upon. And here I just wrote out the expectation, same thing in a little bit different way. So I kind of prefer this like a expectation, just specifying the random variables. And if you can expand it out into like a iterative, iterative expectation, you can kind of see that you first sample from X, which is from the data, and then the Y sampling conditional on the X, you use the policy, the language model to generate Y. Policy is always a conditional probability distribution, so that's kind of what it's done. So I think this is clear to me, but I haven't seen anyone doing this way. So if you don't find it useful, just forget about it. Let's explain it in English. So first, we initialize the policy model parameter to doesn't happen this way, but I think the most common way is to initialize with SFT or the instruction fine-tune checkpoint. And then we sample the prompt from the Eclipse data set, hopefully the same distribution but held up from the RM training prompts. And third, we generate this completion, conditioning on the prompt and using whatever this current policy is, and then compute the reward with the pros in your model and backpropagate this policy, update the parameter, and repeat. So this process, I think, is the real part, and most people from the language background, like myself, this is the kind of the thing that was missing. So yeah, I think that hopefully that made it clear. And that was the vanilla version of the post gradient training. But as with anything deep learning, we need to do that doesn't work like out of the box that well. So we need to add some tricks. And one of the tricks in the GPT paper is this scale penalty. And what that means is that the goal is to prevent over optimization to the RM model, which is kind of vague and different. So here is just the scale divergence is between divergence, not distance, of two probability distributions. And the two distributions that we care about is the initial one, the SFP, which is a reasonably good language model, and then the current policy, which can go to anything. So we just want to make sure that regularize that the policy doesn't change too much, but we also want it to change. Otherwise, why are we training it? So we control the parameter and put it into the expectation. So the scale divergence can be expressed in like expectation with respect to one distribution of that over the other one in log. So that's the scale inside this expectation. So that can be one trick. The other trick that I mentioned about is the pre-training loss. You can add in the pre-training loss to minimize the brain damage, and that's the whole objective function for the instructor GPT paper. And let's see the results of this. So I think this was really surprising to me. So let's try to unpack this. We're trying to see model sizes. We're talking about GPT 1.3 all the way up to 175, the GPT-3 model. And the baseline, we're doing like we're asking humans which one's better, which model configuration is better. And the baseline that we're comparing against is the SFP 175. So GPT-3 instruction fine-tune on that, and that is the baseline, even for 1.3D model, 100 times smaller. And we can see that the win rate beyond 50% is better. So that the yellow one, 1.3D after this RLHF is preferred, not maybe not better, but preferred than the 175, only fine-tuned the supervised fine-tune model. This, I think, really kind of shows that if you want to use language model for an API that humans really want to use, this RLHF seems to have a significant value that crosses the scale of like 100 times, which is almost always impossible. So yeah, I think this is really the key result. Yeah.
There's one question about the scale,
Oh. Yeah.
What happens if you don't have result?
If you train, like, I think so the policy learning rate also exists there. What can happen is like the reward can be hacked in that there might be something that reward model likes that is against the human preference, like say just longer ones are preferred for some reason. Then if you don't try to like if you just generate much longer than SFT model, then this term might be higher to prevent that kind of thing. But if you don't, then it can become anything. And maybe if you train long enough, then it can just become like a completely reward hacked and it's not even language model. Then it doesn't even generate language, but that will be really it will result in really high scale divergence here. So is that try like make it you're still language model even though you're being RL trained. So that's kind of how I think about it.
You know, if they have any instruction
From Instruct GPT, or maybe I can show you. I think there's one plot. It's not like great, but yeah, I have one thing about reward hacking. So yeah, we just saw very good results on the RLHF, and so to summarize the strength of RLHF, because not everyone likes RL, and especially on the language side. One thing that here are a couple things. So whole sample is generated by the policy and the reward is on the whole thing. Compare that to instructive fine-tuning, where when we do the transformer, we do teacher forcing, always do the teacher forcing, meaning that the signal, learning signal is kind of at the token level, whereas in the RL we do at like a sequence level. Not like exactly correct, but I think that's kind of a intuitive enough of a distinction. And then the thing I mentioned about the objective function being learned, I think this, in my view, is the biggest difference, and we'll get into a little bit more on that. So even with the strength, there are some weaknesses, and because RL is hard to get right. And RLHF with like very, very big policy, like 100 billion parameters, even harder. So there is one paper. This is actually a very good paper I recommend. This is another one from OpenAI 3 years ago, which is about summarization. So summarization is also a very good thing that benefits from RL, because if you're trying to summarize from a long text, then there's no single answer that is correct. So that's kind of motivated them to look at this RL, and then whatever humans prefer, that is correct. And we don't know how to measure it, but if you give me two summaries, I can give you which one is better. And that's kind of the core work. And they actually laid out all the RLHF, I think this paper, and then InfraGPT follows almost exactly on this. And this plot is from that. So this scale divergent term, I think that each plot comes from different models. So you use like a small beta type of parameter, then you don't really penalize much, then you can have like a much larger scale term. And then so each are like a different model, different optimization schemes. And the dotted line is the RM prediction of what RM says fraction. Oh, I think there's two completions and which one is preferred. You ask RM and you ask human. And here we can see that if you don't penalize much, they actually diverge. The reference summarization is actually preferred by the RM, but humans don't like it. And they are negatively correlated if you go too far. So this is kind of I don't know which hacking has happened, what the model has, maybe like the comma, in the model like comma or something, weird things can happen. And so that I think is kind of why we need that tail term. But I don't think that's the only way. There are probably other ways to regulate this. But again, new field, and I think we are just learning it. So, and because of, I mean, RLHF is really hard to get, right? So many people don't actually like it. So I'm trying to here convince more people that we should keep studying this RLHF. And I think there are many reasons, and but I will talk about this objective being learned. So, and maybe the other one is RL, we can do negative examples much better than supervised learning. So supervised learning, we say, this is a good example, you learn that, clone that. Whereas RL, this is good, go up and down like that. So that's one thing. Let's focus on this objective function. So in almost all supervised learning or self-supervised learning, we use mental likelihood, social entropy loss, and that I think is too strong of an inductive bias that we are giving to the system. And learning this objective function instead of using this prescribed function is a paradigm shift almost, and there's a lot of room for improvement. To illustrate this, let me just let's go back to like a history of like a learning systems. So if we go all the way back to rule-based systems, this is kind of what happens. This is like adopted figure from the deep learning textbook. So we have input, and then we have like a hand-designed program that said for this input you output that. There's no learning process. So that's the rule-based system. Classical machine learning system changes input, and then we design features and design those feature engineering. And then this part, the thing that gets learned is the mapping from the final feature to the output. You can think about the religious regression, the weights are that mapping. And then once we have the output, we use hand design of function like a percentile or maximum likelihood, and we use the label for that and then train. That's kind of the classical machine learning setting. Deep learning, at least for, oh, this is a spoiler. This it's just out of control. Yeah, so deep learning, at least for like a self-supervised learning and supervised learning, this is what happens. The only difference between the one above and this one is that features are learned. And this is more generally the representation learning idea. And deep learning, we do it in a particular way of learning hierarchical representation. But that is at the high level, what is different. And so learning neural net is like one way, but more important distinction is that we are using learned representation. And that made a huge difference, right? As we can see how deep learning took off. And so if that change made that much of a difference, when not do more and make it more end to end? And if you look at this, the only thing that remains is that, so maybe, I mean, there's one more thing, like optimization can be done, but I think this is the next natural next target. So RLHF is just one instantiation of that. So instead of the hand design loss function, let's use learn the loss function or the objective, which is the negative reward model. So that could be another paradigm shift from this. And I think when we do that, there's like a lot of room for improvements. Especially when we are thinking about this deep learning system. Nothing that I say is like may not be correct, but it's my intuition. When deep learning strength is really in the scalability. And when we start out some field, we need to give some inductive biases, like things that we put into make progress faster. But as we scale up the system, we should remove more of inductive bias. Otherwise, that becomes a bottleneck in scaling. So a lot of the progress in deep learning has been like removing the inductive bias or replacing with the more general one, scale up and see what happens. And so at this point, as I pointed out multiple times throughout this lecture, we are trying to teach models that are really vague and abstract behaviors. And that I think is now this is the loss function is the bottleneck, and we should change that. And so from that perspective, RLHF is just one way of doing it, but I think it has a lot of room for improvement. So what this yeah.
Talking about this more generally,
Yeah.
That term couldn't make sense if we have fields where like there is an objective field. Like NLP, there's always like natural language particular like ambiguity.
Yeah.
If you take like sounds, like we know that something is good.
Yeah. Yeah. If what you want to get out of is like answer, but if you want to get out from the model, what field of science you should tackle and how and things like that. I think yeah, that could be, but yeah, definitely like if there's been math, like you don't want to do that. Yeah. Yeah, but even for math, you can derive to the same answer, but you can prefer one reasoning to get there than the other. So I think there's still like quite a bit of room. So yeah, just graphically, this is something bigger about like I mean, this is probably like very obvious to many people, but some people don't find it obvious. So P4 neural net and logistic regression are very similar in that P4 neural net is logistic regression but learned feature. That simple change made quite a bit of a difference. And we go from like IBM, Deep Blue, I think this is the expert system rubrics, and then SVM. I actually don't know any like a notable example because this was before me, but let's say some SVM based on really popular model at the time. And we go from that to GPT-3, one of the best self-supervised learning systems. And now, if this is enough of a paradigm shift, what can we get? I think this is really exciting, and that's why I once I realized this, I thought that maybe RLHF doesn't work as well for now, but changing this to more of a learned function seems to be the more principal way. And I'm really excited to see what's going to happen in this question mark.